So one of the areas that we want to kind of start with here is one of the foundation of where the wire comes from. Core covered the stainless steel product line. The nitinol team did a beautiful job with nitinol. Our assembly team actually supports our DFT wire and high performance alloys. And many folks are very familiar with stainless steel. You know that, hey, yes, it has to have a minimum of 10.5% chromium. In order to qualify as a stainless steel, that's what gives you the oxide layer, leading to improved corrosion resistance. At times, there's blended a little bit of molybdenum or cobalt into the material that may enhance some of the properties. But at the end of the day, when folks are engineering a device or need additional performance out of the material, you'll turn to a high performance alloy. A couple of the standard alloys that we routinely support throughout the industry are shown in this table. You may recognize some of those from our website, but the first couple on there being 35NLT and MP35N. I'm not going to cover in detail here. I actually have a couple slides following that will talk about some of the similarities, how they're set up, and some of the differences. But just please know that they're a multi-phase alloy, meaning that they've got more of a complex grain structure that allows them to really impart both strength and ductility at the same time. They, as well as most of the alloys on this list, are cobalt-based, and they have about 35% nickel, hence the 35N, as well as 20% chromium, so roughly twice the amount of chromium as stainless steel, leading to improved corrosion resistance, and also 10% molybdenum. So right below them is L605. L605 alloy is another cobalt-based alloy. However, it does have about 15% tungsten in it, which leads to extremely improved high temperature performance. It also has 20% chromium, which gives it its corrosion resistance, and it has a little bit lower nickel content. For metals 1058, directly below there, is known according to the ASTM 1058, but in the industry, you may recognize some common trade names such as L-Jaloy or Finex, but it roughly has about 16% iron in it, and it originally was used in marine applications due to its corrosion resistance in marine applications, watches, those type of things. It does find its way into many different medical applications. Fort-Wayne metal 1537, the last one on this list, is a cobalt, chromium, molybdenum material, so it's a CCM. It is widely used in orthopedic markets, also spinal trauma, and also with dental devices. So as promised, we will press in just a little bit here on MP35N and 35NLT. Again, the MP references multi-phase, 35N references 35% nickel. Both MP35N and 35NLT are very similar in a number of ways. They are both based on the ASTM F562 chemistry, which I mentioned on the previous slide. Both of them have similar melt processing. So they use vacuum induction melt, VIM, followed by a vacuum arc remelt. Both of them, of course, meet the ASTM F562 specification. However, there is some significant differences. So the titanium content in MP35N is up to 1% max, and with 35NLT, it is limited to 0.01%. So 35NLT, or you may think of the LT as low titanium, that significantly limits, so about 1/100th of what the max composition in MP35N. And the next slide will start to press into why that is. So in the 80s, Fort Wayne was working with many medical device companies and trying to improve the performance of our materials. And some of the things that limited the fatigue performance of MP35N, which was an industry-leading material, was the presence of titanium nitrides and titanium inclusions in the actual melt material. And so Fort Wayne worked with our industry partners as well as our supply chain to design a melt that allows us to remove a significant portion of the titanium, and thus it imparts very different properties in the fatigue life. In the picture in the upper left, you can see what a typical titanium inclusion looks like in MP35N. You can see that there's a lot of jagged shapes that lead to stress risers in the material, leading to wire fatigue breaks. The picture right next to it, that circle, is what a typical inclusion looks like in 35NLT. Not only is the inclusion much smaller than what we find in MP35N, but the shape itself significantly reduces the propensity for stress risers within the material. As evidenced in the table below in the chart, you can see the red trace is for MP35N. The blue trace is for 35NLT. And what the table shows along the x-axis is a logarithmic scale of the number of cycles that a material can impart or can survive during a cyclical rotary beam fatigue test. So for those of you that are not familiar with rotary beam testing, you can basically take a wire, you put it in a U shape. One side is chucked and hooked up to a motor that spins the material. The other side of the U is pressed into a bearing and it's allowed to freely rotate. So as the motor turns the chuck at roughly 3,600 RPM, you can envision that wire rotating in that U shape. Each rotation is considered a cycle. And because of that shape and the rotation, it's like flexing the wire back and forth. So what the table shows is at a given stress level, which is on the vertical axis, you can see that the trace for the 35NLT is to the right, and it is upward or higher than the red trace for 35N. And so what that shows is that at a given stress level, the 35NLT survives roughly, well, it's multiple orders of magnitude, up to 10x, more cycles than what the MP35 is. Or you can say at a certain fatigue life or a certain number of cycles, the 35NLT is able to survive a higher stress level than what the MP35N is. What this led to was a significant improvement in the performance of material and coiling for pacing leads, the proliferation of use into neural stimulation leads, and over the years, 35NLT has replaced many applications for MP35N. So part of what I said we were also going to cover is our DFT wire. Our DFT wire combines the properties of dissimilar materials into a single wire system. So basically you can take the advantages of two different materials or three and leverage those within a single wire. Where this originated from, down at the bottom, you can see that Fort Wayne introduced a material called DBS into the industry in the 60s. And basically DBS is where we took like 6 wires of stainless steel that were wrapped around a core of silver. That strand was then brazed, which allowed the silver to proliferate amongst the different stainless steel filers in that strand. And that improved the conductivity. So we were taking the fatigue and the mechanical properties of stainless, joining it with the conductivity performance of silver. And that DBS material was drawn to final size and used in many different CRM applications. Well, once MP35N was introduced to the industry in the early 80s, we started to see a significant improvement in the fatigue life. And so we wanted to be able to leverage the fatigue performance of MP35N along with the conductivity of silver for CRM applications. And so Fort Wayne developed a system to be able to provide, to take a sheath, an outer sheath of MP35N, and we would fill that with a core with silver, or it could have been platinum for radiopacity. But those 2-part systems or even a 3-part system allows you to take advantage of the properties for each of those materials. This DFT wire can be drawn to similar sizes as other materials, such as it can be drawn to 0007, and we provide all the way up to 0.0126 inches. Various strength levels can be developed by a cold wear profile. And of course, we can offer DFT wire in various forms, such as round, flat. We can do shaped. We can give it different treatments to optimize the performance for your application. To finish the journey down at the bottom, you can see that DFT wire was introduced into the mid 80s, and then it was enhanced when we started leveraging 35 NLT in the early 2000s. And then finally, in 2019, we introduced the process, a new process for how we prepare the DFT wire, which further enhances its strength and fatigue life and overall performance in the applications.